Hello, welcome to Sustainably Smart. I'm your host, AJ Makarapa, where cutting edge meets a sustainable future. I work in the intersection of Internet of Things and renewable energy, and today I brought my guest, Lukša Kujović, who works at Crest, which Crest works as, well, better explained, this is your field, your department.
Well, thank you very much for the introduction, AJ. First of all, I'd like to say that I'm honored to be the first guest speaking here. I really appreciate you inviting me, and I look forward to discussing this topic further. So, just to give you a little bit of a background, I studied in Eindhoven, and Eindhoven University of Technology, where I obtained my bachelor degree in electrical engineering. And then after my BSc, I decided I wanted to sort of diverge a little bit, go into renewable energy because it was something I was always passionate about. And then I came across Loughborough University. Never heard of the place before, if I'm being honest, but I'm very happy that I did find it because it truly does feel like a family being here. And more specifically, Crest. Crest is the Center for Renewable Energy Systems Technologies, and it's based here in Loughborough. And it focuses on, as you would expect from the name, it focuses on a variety of different renewable energy technologies. But myself, I decided to stick to solar power. And now solar power for me, it stems from my undergraduate bachelor end project, where I was studying the effect of increasing distributed energy resource penetration in the distribution network. And my distribution energy resource, I'll call it DER for short, was solar power. So that's where I first got introduced to sort of solar power as a technology. And I modeled a solar system to study the effect of increasing the solar power penetration into an existing distribution network. And while my research focus there was on mitigating the issues that arise due to increasing that penetration. So by increasing the DER in the existing distribution network, you get certain issues such as overvoltage, which I'm sure you're aware of. And what my research focused on was providing a method to mitigate these issues by adjusting the load in the distribution network. And this allowed the feasibility of the solar system to be improved. So this is where I first sparked the interest in renewable energy. And then, as I mentioned earlier, I came across this great course in Loughborough where I did my MSc. And in that MSc, we covered a variety of different technologies, ranging from solar power, wind power, hydropower, bioenergy, the whole spectrum of renewable energy. But for me, solar power really stood out. And if I'm being completely honest, I wanted to end my academic journey there and my master's degree.
I was in a similar position as well after I graduated with my master's in communication systems. I don't think I was going to do a PhD because a PhD requires a lot of funding. Well, how did you manage to get the funding to do a PhD? That's the main thing that's a bottleneck for most students when it comes to doing a PhD. I remember my fourth year, there was the similar situation. How did you get your PhD funded?
Oh, that's a great question. Well, during my master's project, which I thoroughly enjoyed, it was on thin film cadmium telluride photovoltaics, which is a second generation PV technology. And just to give you an idea, 95% of the PV market is made up of silicon modules, and the remaining 5% is mostly made up from thin film cadmium telluride. And because I was working on this project, there's this company called First Solar, and they are the leading company when it comes to thin film cadmium telluride photovoltaics. They're based in the US, and they had some funding available for a PhD student. And I was lucky enough to be provided with that opportunity. My supervisor, Mike Walls, is the primary reason why I stayed, because he approached me with that opportunity, and I was very grateful for that. I received the funding to do my PhD. And going back to the decision of the PhD, as I mentioned earlier, I never had the intention of doing a PhD, but because I enjoyed doing the master's project so much, it was very much a lab environment. I was spending most of my days in the lab, and I was studying the stability of different N-type materials to be used in photovoltaics. As I'm sure you know, a solar cell is made up of a P-N junction. So you have a P-type material and you have an N-type material. The N-type material being the one that has the dominant carrier being the electrons, and in the P-type material, the dominant carrier are holes.
So in essence, what we're trying to break down is just the way how electricity flows from positive to negative for the solar cell.
Yes, and you need that. And without a p-n junction, you will not have a working cell. So what my
correct.
Yeah. What my master's project focused on was just the N-type layer. So what we did was we prepared a variety of different N-type materials. So mostly zinc oxide based, but we had some tin oxide, a variety. I don't want to get into details now, but in any case, we had a full range of materials. And out of those materials, what we did is we took unencapsulated materials, which, by the way, all solar cells that are out there in the field, they're all encapsulated. So they're not directly exposed to the harsh conditions of the environment. But what we did was to test for the stability, because, you have a lifetime of a solar cell. What is it? It's around 25 years, 30 years.
Is it 25 and 30 years? But just to ask so I can remember, so we give it a bit more structure, is that you said 95% of the market is filled with silicon?
Yes.
And 5% is with thin film. What's causing that disparity, and why is the market dominated by silicon at this moment?
Well, that's a great question. Well, for one, silicon is an older technology. So silicon solar cells sort of gained traction in the 1950s, whereas thin film cadmium telluride only started in the 70s. So right away, you have a sort of a pretty noticeable difference in terms of time that was spent researching these materials. And silicon is used in the entire semiconductor industry. So it's a very well-researched material. And because of this, so silicon had a bit of a head start, right? And for that reason, silicon also has, on average, higher efficiencies than thin film modules, specifically thin film cadmium telluride modules, or CadTel for short. And because of this efficiency, the higher efficiency, it's more attractive for consumers, right? I mean, we're all about efficiency. We're trying to get as high of an efficiency as possible. So naturally, people are sort of drawn to that.
So the future is thin film.
Well, I'm a little bit biased when it comes to this topic, as you might expect, but there are good reasons for it, and there's a lot of research that supports this. The reason why thin film is a lot more attractive, in my opinion, and also a lot of other people seem to agree, is that it requires around 99% less semiconductor material. So, and this largely comes down to thin film materials, such as cadmium telluride, having a direct band gap, whereas silicon has an indirect band gap. So what that means is the absorption coefficient of cadmium telluride is much higher than the absorption coefficient of silicon. So what that means is you need less material to fully absorb light. So for thin film CadTel, you only need around 1 micron to absorb 99% of the light, right? Whereas for silicon, for instance, to absorb that same amount of light, you need around 200 microns. So right away, there's a huge difference. We're talking about, 3 microns, which is typically the absorber thickness for cadmium telluride, versus 200 microns. So right away, a huge difference in terms of the semiconductor material requirement.
Okay, interesting. Because you said the lifetime of most solar panels are 25 years. And I know that I've done my own calculations for payback period to see what's the energy efficiency we can get back and see when we can get our internal rate of return of our investment. On average, it's about 7 years. So what would it be for these thin films then?
Well, for thin films, what I can say in terms of the embodied carbon and in terms of the sort of manufacturing processes that go behind the manufacturing process is significantly lower than the silicon modules. And this goes once again back to the fact that you need less of the material. So for silicon modules, you need around 3 to 4 days to manufacture a module, and typically it involves more than one lab. Whereas for thin film technologies, they can be manufactured within 3 to 4 hours. So we're comparing days to hours here. So ultimately, the manufacturing costs are lower, and it also requires less energy. So because of this, the energy payback time for thin film technologies is noticeably lower. There's a paper from NREL, which is the National Renewable Energy Lab. And by the way, they have some great papers out there. So if anyone does want to learn more, definitely, if it is an NREL paper, you can definitely trust those results. But anyway, they do report that the embodied carbon in thin film CadTel is around half the embodied carbon in silicon. So whereas in silicon, a lot of the embodied carbon comes from the semiconductor material.
Oh, nice.
Whereas from CadTel, it mostly comes from the actual frame, from the glass, more about the putting the module together, not from the absorber material.
So then where's the bias then when it comes to the thin film and silicon? Where is it more applicable than the thin film and the silicon? What's the difference between them? What causes your bias? Yes.
That's a great question. Well, it really does depend on the region as well, because one thing where thin film CdTe does excel in is in warm climates. There's a term called the temperature coefficient, and what this basically tells you is for every degree Celsius that you go above the standard test condition temperature, which is 25 degrees Celsius, your efficiency will reduce by a certain percentage. Now, for silicon-based modules, that's around 0.4% per for degrees Celsius, whereas for CdTe, that's half. So it's around 0.2% per degree Celsius. So if you have a 300, let's say you have a 300 watt module, and you take silicon, for instance, so 0.4% in that case would be around 1.2 watts. So for every degree Celsius that you go above 25 degrees, you're losing 1.2 watts. And that's simply just from the temperature. So naturally, if you place a cadmium telluride and a silicon module side by side in a warm climate, let's say somewhere in the Middle East, the power loss you'd get due to the temperature would be higher with silicon. So I always say CdTe, it definitely is more attractive in warm climates.
Warm climates, such as developing countries like I'm from Botswana, we have desert. 70% of the region is a desert, and it's quite hot. The climate is quite high. So would you say this is an attractive option, a solution for these developing countries to implement renewable energy and cadmium telluride, if I'm correct?
Yeah,
That's the one you should be implementing.
In the ideal world, yes. Now, I'd say that there is one limiting factor in that in terms of silicon, it's a lot more accessible, I want to say, currently. I mean, I'd like for that to change. I'd like there to be more cadmium telluride manufacturing sites. But as it stands right now, the only commercial cadmium telluride company or provider is First Solar. So as you'd expect, you have, so in China, you have a lot of companies working on silicon modules, right? And so if you're comparing the silicon market to the CdTe market, it's easier to get your hands on some silicon modules, right?
Yes, I agree with that.
So in that case, it comes down to importing the modules, in from a cost perspective. But there is a metric called the levelized cost of energy or levelized cost of electricity. And when comparing these numbers, and so just to clarify, are you familiar with?
Yeah, levelized cost of electricity. I do the same calculations for my own solar systems that I'm patching for my sustainable fish farmings that I'll be deploying in Botswana. Is that?
Oh, that's great. Well, this will be nothing new to you, but in any case, we're comparing the cost of electricity, right? That's what we're all interested in, because the lower the cost, the faster we can accelerate the PV deployment, especially in developing countries. So having a lower cost is obviously very attractive. Now, in terms of the levelized cost of electricity for thin film versus silicon, the thin film cost of electricity is lower. Okay. Once again, tying back to the manufacturing costs, less material, and so on. So that's very attractive for developing countries. But obviously, you have to take into account the availability of these modules.
So there's this now, put a hypothetical scenario. Say that I wanted to start manufacturing these in Africa myself. Is that something viable? Would it be viable? Which materials would I need to import? What labor would I need? As you work in a lab environment producing these cells on a regular basis, so as to stop Africa's reliance on importation, let's start now creating for exporting.
That's a great question, and yeah, unfortunately, it's not always very easy, especially for the manufacturing of these cells. They are very sensitive, and you do need. I'd say the startup cost would be quite high to begin with. And making whole modules from scratch, that's something which, I mean, we haven't really tried ourselves. So I can't say on a module scale that that's something which would be feasible, at least in a relatively short time frame. But in our lab, we focus on research scale cells. So our cells are, we work on a substrate which is around 5 by 5 centimeters in size, which is very small compared to a module, right?
Okay.
So making on that scale, on a small scale, I'd say that's doable, but scaling it up to, meters and meters of modules, that's something which I think will be quite challenging.
So what are the standards for measuring these solar cells that you're creating?
So standards for measuring, we have the standard test conditions, which basically the reason they're in place is so that we have a reliable way of measuring cells across different locations. So if you let's say you're trying to measure the cells outside, if you try to measure a cell somewhere that's very sunny.
Also, there's a difference between your indoor photovoltaic systems and your outdoor photovoltaic systems.
Definitely. I mean, even less dramatic than indoor and outdoor, even just your geographical location, that could have an impact. So one thing that's really important is to have a standard test condition. And in terms of measuring solar panels, we always measure them at the AM 1.5 G spectrum at an irradiance of 1,000 watts per meter square. So this is so that, let's say you have some solar panels in Botswana and I have some solar panels in Sweden. If we go outside and try to measure the same cells, we're going to get different characteristics.
Okay.
So for that reason, we always measure them using the same conditions. Also at the same temperature, even so 25 degrees Celsius. So going back to the temperature, if you measure it in a warmer climate, you're obviously going to have not as well of a performing device as if you measure it in a cooler climate. So it's for this reason that we have this standard test condition.
Standard test conditions. So, what I've gotten from this conversation is that manufacturing costs are lower with thin film. They have better efficiency.
Well, for thin film, the efficiency is still lower than silicon, but in terms of the theoretical maximum efficiency, it's higher for cadmium telluride. Now, I'll just briefly explain. In terms of the theoretical efficiency, there's a term called the Shockley-Queisser limit, and what this does is it presents efficiency as a function of band gap. So band gap is a characteristic of the semiconductor material. So for silicon, it has a band gap of 1.1 electron volts, whereas cadmium telluride, which incorporates selenium, it has a band gap closer to 1.4, even 1.39. Whereas the ideal solar cell, so if you try to think of the most perfect solar cell to get the highest possible efficiency, which is 33.7%, for that solar cell, you would need the band gap to be 1.34. So right away, when we're comparing silicon to cadmium telluride, you can see the difference. Okay. 1.1 to 1.34 is a bigger difference than 1.34 to 1.39, right? So cadmium telluride as a material is more suitable in terms of absorbing the photons. So
photons coming from light.
Yes.
Sunlight.
Yes, exactly. And so from a theoretical perspective, cadmium telluride, you would expect to be more efficient. But because silicon is an older technology, a lot more research, a lot more time has went into it, silicon currently has a higher efficiency. So in that sense, silicon is more attractive. But as I mentioned earlier, there are some very attractive points for thin film technologies as well.
So the development is definitely then for us developing countries, just to emphasize on how can we get these cadmium telluride working for us in our regions, because they were more stable in the hotter regions. Is that correct?
Yes. I mean, in warmer climates, you would expect the power output to be closer to what it says on the nameplate, basically. But even then, even these solar modules, they go up to very high temperatures. Just because it's, let's say, 30 degrees on your weather app, the solar modules go significantly higher than that. So that's something else that always needs to be taken into account. And in terms of stability and degradation, you have standards for that as well. So there's an IEC standard that we use in the lab to measure the degradation of these materials. And what that does is basically we try to accelerate the lifetime. So we place these materials in both ultraviolet and damp heat.
Also to the harshest conditions, you test them just to show that durability.
Exactly. So we go up to a period of 1,000 hours, unencapsulated. So they're directly exposed to moisture and high temperatures. So damp heat basically means a temperature of 85 degrees Celsius at a humidity of 85%. So you'd expect these are very harsh conditions. You don't see this on a daily basis pretty much anywhere. But we do this so that we can replicate or try to replicate in a reliable way the 25-year period in a much shorter time, right? We can't test them. It's not easy to test new materials that are going to be out there for 25 years, right? So you need to have a standard to measure that. And that's what we do here in the lab. And in terms of silicon, I mean, I'm not saying it's not a stable material. I'm not saying that at all. I was just referring to the temperature difference.
Okay.
So in terms of temperature, cadmium fluoride is, I want to say, more suitable. But yeah,
One problem that we have as well in our developing countries, especially the Middle East, where they're going to invest in this, we have dust, which unfortunately is affecting the quality of solar panels. If there's a little speck of dust, the efficiency drops a lot. These are a lot. So can you please explain it to the viewers a bit more?
that's right. And yeah, there was the correct term is soiling, and for that reason there are anti-soiling coatings, and it's a very good point, because silicon, so the commercial modules, they're mostly coated with porous silica, which is a anti-reflective material. Now, this anti-reflective material by nature is hydrophilic. So what that means, it makes because it has a low water contact angle, it makes it so the water wants to stick to the surface. And what you need is something hydrophobic to have a high water contact angle to make it so that the water can just easily slide off, right? And now the issue with the AR coatings, anti-reflective coatings.
Also, I've seen that some people have designed self-cleaning devices. I think the next list will explain that too as well. So
yes, that definitely is a thing. And I mean, the concept is, the idea is that you have a slightly tilted panel. So if there is rain, if there is any water that gets in contact with that surface, the water will collect the dust particles that are on the surface, and it will just sort of just slide down, right? And the issue with the anti-reflective coatings is that obviously you need to clean the panels. Now, in dusty regions, people clean panels on a daily basis, right?
just soiling.
So exactly, so using brushes, which are quite abrasive, and we have a lot of evidence to show that. But in let's say in the UK, they only clean panels, I want to say, maybe twice a year. So very big difference there. So you would expect that the climates or the regions which are more dusty, have a lot of sand, you need to clean them on a regular basis, on a daily basis. So what that means is, every time you clean these, because the brush is abrasive, you scratch off some of the anti-reflective coating. And then in the end, you'll be left with just the glass. So no AR coating. So right away, you could be losing out on 3%-ish relative in terms of efficiency. So that's a huge difference. And for that reason, our labs, I have one of my colleagues, Adam Law, he's developing a multi-layer anti-reflective coating, which has proved to be a lot more stable. So instead of just using silica, it uses zirconia as well in alternating layers. So it's a multi-layer. And that has proved to be a lot more durable, which can withstand these abrasive brushes.
Well, it seems like you know a lot about what we need to do in terms of what development you need to do for future solar cells. So tell me about your PhD experience then, of how you're currently researching, your papers that you've published, and publications to back up the research and the evidence you're giving today.
Yeah, no, luckily I've been able to publish a couple of papers. We have a very great team here at Crest, and it's a very collaborative environment. So since I joined, I got involved in projects which honestly I never thought I'd be involved with, and that's the beauty of it. You collaborate with your colleagues. You start learning, and by doing this, you're not only learning about the PhD topic that you signed up for, you're learning on the PhD work that your colleagues are working on. So ultimately, it's a great way to expand your knowledge. And what we've done is we have this one conference which happens once a year. It's called the IEEE PVSC conference, and each year we go and we present our work, and we get a lot of feedback, and we basically find collaborators for other work. So we work with, as I mentioned earlier, NREL. NREL is one. Yeah, it's a great company based in the US. First Solar as well. Other universities across the world as well. So this makes it a lot easier to get the papers published out there, and you can find all of our papers on there. And just overall, like the experience, if that's what you're asking me for, I'm enjoying it more than I thought I would, if I'm being honest. I think a huge contributor, a huge reason for that is that the environment at Crest, it has a very much of it almost feels like you're working at a company, but at the same time you're working at a university.
So university have a big crucial role in developing a sustainable future, so for sustainable innovation. So do you plan to see yourself in academia, or do you want to go back into industry?
That's a great question. I ask myself that every day. I'm open to both. I do enjoy academia thoroughly. But during my time in my first year of the PhD, I spent 3 months working at First Solar, actually, the company funding me. And the 3 months there, they were funded by actually an EPSRC funded network, which at the time was called SuperGen Super Solar Network Plus, which is free to register. And currently there's a very similar network called the SES Network Plus, which is also free for anyone interested in solar energy systems. You can register there. And what it provides is it provides funding opportunities for aspiring students, people that are doing their PhD, to get some industry exposure. And also they help fund conferences and so on. But anyway, I was lucky enough to get 3 months worth of funding from them to spend 3 months in California at the First Solar R&D Center, which is called the California Technology Center. And there, I really enjoyed the industry atmosphere, actually.
Okay.
So because of this, I'm torn between the two. You know, I really enjoy academia, but equally I enjoyed working at First Solar as well.
So tell me about your day-to-day, about your secondment, how it went.
The secondment, it was great. So similar to the lab environment here, it's a bit of a mix. You know, you spend half the day in the lab, and then half the remaining day trying to figure out the results, right? I mean, there's a lot of analysis that goes behind the scenes. I mean, what we publish, all the papers that you can find, it's only scratching the surface of what actually goes behind each paper.
You've published a lot of papers, and now that you had PhD experience, what would you describe about it?
I mean, overall, like I said, I enjoyed it a lot more than I ever thought I would, if I'm being honest, because you hear all sorts of stories. But one thing that's true is no PhD is the same. You know, depending on who you talk to, someone's going to have, you know, the time of their life. Someone might have a bit more difficult. It really depends. I mean, a key thing that really makes a big difference as well, from the stories I've heard, is the supervisor. Supervisor plays a crucial role. I was very lucky with my supervisor that I have. He's provided me with great opportunities, a lot of really good support. So if you have that, I can guarantee that, you know, it will be more of an enjoyable experience. And
before I made my PhD choice as well, the number one advice I got was that supervisor is the most imperative thing to select. Do your research on that. That is your make or break if you'll be a successful researcher when you get your PhD.
Definitely, I couldn't agree more. And in terms of your PhD, you mentioned earlier that you never had the intention of doing it initially, and then now you ended up going down that path. Are you happy? Or how are you finding it so far?
Overall, the PhD has opened doors for me, as in that I came to Loughborough University with an entrepreneurial ambitions, as in I graduated from University College London and then started my own startup. I quickly realized that these things require a lot of money and a lot of investment. And luckily, I was still a top achiever in my home country. They've been funding me since my A-levels, and they sponsored my undergrad and my master's. And after I started my startup company, talked to the Botswana Innovation Fund. They were willing to fund my business, but then I was like, wait a minute, if they're willing to fund me, I'm going to progress my idea and take it a bit step further. And I came to Loughborough University. Loughborough University has opened doors for me in the sense that has given me space for the incubator to develop my business, to publish papers. I published my first paper last year in wireless communications and did very well, won Best Presentation Award in China. And how I see the fusion of my research with renewable energy is that it's important that our Internet of Things devices that we will be implementing in the future also be empowered in a sustainable way in the transition that we're making between fifth generation network and sixth generation networks. So I've really enjoyed this experience being a part of Loughborough University, and it's a top institute, and it's also made me an even better person overall, is that there's a lot of athletes here that have encouraged me in a way that has given me a lot of mental grit, which was something you need as well for the marathon that you run, doing a PhD, running a business.
Well, congratulations on all of your achievements, AJ. That's very impressive, and you seem like a very motivated guy, and I'm sure you'll really make it far in this field. So, and all the best with that.
Well, I appreciate that, Lukša. That's but there's still a lot of work to be done, and I wouldn't be here without the Botswana government, my supervisor, and most importantly, my parents. Well, I'm honored to have you today as one of my guests. Bringing a pedigree of knowledge has really opened up the landscape of what I can think about what we can do for renewable energy. To find our contact details, if you want to talk to Lukša more about PV-related equipment, His contact details are in the comment description. Please leave comments as well. Asking any questions, we'll get back to them. And for my contact details as well, I've left them as well in the description. Thank you for watching Sustainably Smart, by cutting edge to sustainable future. Thank you.
Thank you very much.